In this video, we will study two color balls combination probability for the case of sampling of two only. So let's assume we have a population of 20 person, and instead of giving them names, we can just give each person a number. So now each person is known by his number rather than his name. And let us assume that we are interested in specific characteristics in this set of population, such as a person wearing a blue shirt or red shirt. And so now we can represent a person wearing a red shirt with a red object with its name on it. And also we can represent a person wearing a blue shirt with the blue objects with its name on it. And we can do that for the rest of the population. And we keep doing that until we get all the population mapped into two characteristics, and that is blue and red. So let's put all these objects in the urn. And now we don't need the population because the population is represented with these objects. We have the following problem. An urn contains 12 blue balls and 8 red balls. 2 balls are picked up at random without returning the balls to the urn. So the first question, what is the number of all possible outcomes or the number of elements in the sample space? So first thing we do, we number the balls. So we number the blue balls from 1 to 12 and the red balls from 1 to 8 in order to make them distinguishable balls. But we have to remember that there will be balls holding the same number, but they are distinguishable because this is 8 red and this is ball 8 blue. And we may have also here ball number 1 but red one, and here ball number 1 but it is blue 1. Or we can number them from 1 to 20. So both ways will create distinguishable balls. Now let us examine the drawing process. So here are the objects, and we may draw object 11 blue, and after that object 6 red. And now we have a sampling of 2, which is 11 and 6 object. The contrary also may happen. So we may pick up object 6 red, and after that we pick up object 11 blue. And now we have a sampling of 6 11 instead of 11 6. So we can see now that these objects can be picked up in different order. So we conclude that the balls come out of the urn in order, and the actual sample space is composed of ordered elements. So these two differently ordered elements now will be counted as one element. But if we count the element of the sample space in any order, that will not change the fact that the actual sample space is still composed of ordered elements. And in such case, we can use the combination formula to find the number of elements in any order in the sample space, but we have to remember that this is not really the actual sample space. So in this case, we conclude that the outcomes of our probability experiments, they come out in order and without replacement. Therefore, the probability of its event, and we mean by it, we mean our probability experiment, must be solved using a formula which requires order and no replacement, and that is the permutation formula without replacement. So now we face the following question: why is the probability of our experiment can be solved using a formula which requires no order instead of order and no replacement? And this is the formula. We are going to answer this question later, but not in this video. But we have to remember always the relation between combination and permutation. So combination without replacement is equal to permutation without replacement divided by r factorial. So the number of elements in the sample space for the case of any order can be computed from the combination formula under the condition of withdrawing without replacement. So here we have n, the number of objects in the set is 20. So this is the population number, and r, the sampling size, is equal to 2. So we are picking up 2 objects out of 20 population. We substitute that in the combination formula and we get 190 possibility or 190 outcomes. Question number 2. What are the possible joint outcomes from the standpoint of colored balls? So let us say that B represents a drawing blue ball and R represents a drawing red ball. We will use a tree diagram, and in the beginning we have 12 blue and 8 red. So for the first draw we may either pick blue or red, and in such case if we pick up blue, then the remaining object in the urn is 11 blue, and if we pick up red, then the remaining object in the urn will be 7 red. And for the second draw, again we may pick up blue or red, but the remaining object will be 10 blue and 6 red. We are withdrawing without replacement, and this is why each time we draw again we have to know how many objects remaining from each kind. And now we can get the possible of joint outcomes for these two characteristics, blue and red. So we may pick up blue and blue, blue red, red blue, or red red. And these are the joint outcomes. Question number 3. How many blue and blue balls can be withdrawn? Or how many 2 blue balls can be withdrawn? So we have the urn with a total population, but we will divide it into 2 subsets. The first one is the blue subset and the second one is the red subset. So now we are picking up from the blue population, which has a total number of 12. So we may pick up this object and then the second blue object. And now we have a sample of 2 blue objects. So now what is the number of possibilities? For blue and blue, we are combining 2 objects out of 12 only, which is the number of blue objects. And that is combination of 12 objects taken 2 at a time, or 12C2. And this is equal to 66 possible outcome of picking up blue and blue distinguishable objects. Question number 4. How many blue and red balls can be withdrawn? So here is the population, and we will pick up 1 object from the blue population and 1 object from the red population in order to compose a sampling of 2 objects. One is blue and the other is red. So we may pick up blue red or red blue, and now we need to know how many ways for such non-ordered pickup. So we are picking up 1 blue out of 12 blue, and that is combination 12-1, and we are picking up 1 objects out of 8 red, and that is combination of 8 taken 1, or 8C1. But before we continue, let us remember the multiplication principle of two events or sets. If event U has U objects and event V has V objects, then the product U times V or V times U represents the occurrences of both events in any order, and this is the case of the multiplication principle where order is not important. So there are cases for the multiplication principle where order is important, such as this case, and also this case here, but we don't need them now. We need the case number 3 for our combination formula, because combination formula assume no order for sampling elements, and this case in the multiplication principle also assume no order. So going back to our question, we have two sets. The first set is 12 combined 1, and the second set is 8 combined 1, and now we want to know the number of possible outcomes from these two sets. So we can use the multiplication principle by multiplying the number of these events together, and we get 96 possible outcomes. Question number 5, how many red and red balls can be withdrawn, or how many 2 red balls can be withdrawn? So now we are picking up from the red population only. So we pick up the first blue and the second blue, and now we have a sampling of 2 red objects. So we are combining 2 red objects out of a population of 8 red, and that is equal to 28 possible outcome. So we have a 28 possible outcome of picking up 2 distinguishable red objects. So now let us look at the sample space and the events in it. So we have the event of sampling 2 blue with a number of 66 possible outcome, and sampling blue red or red blue with a total number of outcome 96, and we have the event of sampling 2 red with a number of outcome 28. So we divided the sample space into 3 subsets with these 3 events, and the union of all these events will create also the sample space. So we created partition in the sample space using these events. Question number 6, what is the probability of drawing 2 blue balls? So these are the events in the sample space and their names. So now we have the event of 2 are blue, or sampling 2 blue, and the probability is the number of elements in this event, which is 66, divided by the total number of elements in the sample space, and that would give us 0.34 or 34% approximately. Question number 7, what is the probability of drawing blue and red balls? So this is the event we are looking for, and the number of elements is 96 here. So probability is 96 over 190, and that is 0.50. Question number 8, what is the probability of drawing 2 red balls? So this is the event of 2 red with a total number of elements 28. So its probability is 28 over 190, and that is 0.14. Question number 9, what is the probability of drawing at least 1 red? So it could be here 1 red or more than 1 red, which is 2 red, and these 2 events are going to be at least one red. So in this case, the total number of element is 96 plus 28, and the probability of this event is the sum of their probabilities, and the reason why, because they are disjoint events, their intersection is a null set. So probability of the first plus the probability of the second, and we get 0.65 or 65%. Question number 10. What is the probability of drawing at least one blue? So we may have to pick up one blue or two blue, and their union is the event at least one blue. So now their probability is the sum of their individual probabilities, and the reason why, they are disjoint events. So probability of the first, so we have 66 over 190, probability of the second 96 over 190, and that is 0.85 or 85%. Question 11. What is the probability of withdrawing two balls of the same color? So we may pick up two blue or two red, and these two events are disjoint. Their union is the event we are looking for. So the probability of this event is the sum of their individual probabilities, and that is equal to 0.49 or 49%. Thank you for watching and have a nice day.